We talked about the recurrent model of attention, first applied to the original problem, which is sequence-to-sequence modeling in NLP, machine translation, then to vision. And we also mentioned that there are many different applications of this recurrent model of attention to any multimedia type sequence problems. When you're creating a sequence, you can make this algorithm work. Now it's time to talk about this different model of attention. Actually, the model of attention in the transformers is twofold. There's this self-attention and there's this other type of attention in the decoder. So next week, we are going to cover this paper, Attention is All You Need, and we are going to start covering it from the encoder. But before doing that, today, I'm going to make an introduction to the attention module of the encoder, which is the self-attention. So self-attention is, as the name implies, is a mechanism which is in which you use to understand the focus of an input sequence within itself. But why would we need it? Because the focus, the attention type of attention that we're trying to understand in the previous model was between the decoder and the input encoder. So in the output and the input. But this time, these guys come up with this idea that let's model the input sequence in using attention. Then let's feed that attention modeled sequence to the decoder. That's what they say. They say many other things, but we are going to get there first. So I'm going to talk about the different type of attention models where there are no recurrent models, no recurrent attention. This might be confusing to you because the type of attention that we've designed, that we talked about, not we designed it, that Badano designed and we talked about was a mechanism that relates the hidden states of the encoder to the decoder. So when I say hidden states, it's definitely related to some sort of recurrent model, right? But in this self-attention model, we don't have recurrency. We have another way to define attention in the encoder. And they call this model an self-attention. Actually, this is largely inspired by a previous paper in 2016 by Chang et al. Just click it and you'll find the paper. Okay, so let me just click this. So it's here. Let's long-term machinery, whatever. And actually, in this model, the self-attention mechanism is used to encode the input sequence to be used by the decoder, not using RNNs. Both the encoder and decoder will not have the usual RNNs in the transformer. We are going to see it next week. But in the decoder, we will have some sort of feedback mechanism. So we may say that the decoder of the transformer is somehow recurrent. But the thing about the encoder of the LSTM is it is totally non-recurrent, which is a new subject. I mean, there are some nice things about this that we're going to discuss next week. So what I'm going to discuss is this week as the final subject. There is this thing called self-attention in the transformers. It's a different type of attention, but it's still called an attention because it has quite fundamental similarities with the attention we know. Let's learn what this self-attention is so that we will be prepared for the next week's lecture where we are going to talk about transformers. Because the self-attention is the fundamental module in the encoder of the transformer. So having seen it the previous week, will help us to understand it next week. That's what we are doing. Okay, so this paper I just showed you. Sometimes self-attention is called intra attention because it is the attention within an input sequence. It's a type of attention mechanism which relates different positions of a single sequence, if it's a sentence, different words of a sentence, in order to compute a representation of the sequence. So we are representing the input sequence as an intra-relation, intra-similarities of attention. Well, it doesn't seem like the attention that we have seen. So why am I calling it attention? Because the mechanism, actually, the mathematics of it is very similar. And while doing this, I am going to define 3 new concepts which are inherited from the data retrieval database system. So if you're an IS student, you have taken those courses, you know that better than me, the query, key, and value. So this is the attention module of the transformer. It doesn't make sense now, but in 20 minutes, it's going to. The input is, in addition to the input sequence, some sort of matrices, weights, the query weights, the key weights, and the value weights, okay? How am I going to use them, or why am I naming them like this? Just bear with me, I'm going to get there. First, I'm going to define the self-attention without the query key value matrices. So I'm going to call it the plain self-attention. So let's start with this plain self-attention mechanism where there are no learnable parameters, weights. These matrices do not exist yet. So I was thinking that I could write them, but I found this YouTube video. This guy wrote them with his pen. So I've taken his writings. So you can just watch this YouTube video if you want to watch this guy's simple explanation of self-attention. So what we're trying to do is we have a sequence. We have used a type of embedding so that we converted those tokens into vectors. Remember the embedding idea from the previous week. Then we have the attention layer, which is going to provide a context vector for each input sequence. Well, this was the attention mechanism in Badanau's attention, right? We have a sequence. That sequence is being vectorized using an embedding. So for each input vector, I will create a context vector to be used by the decoder. In Badanau, it was the decoder LSTM. So how do I do it in self-attention mechanism? So the self-attention will be the attention not between the decoder hidden state and the input. It will be a type of attention which is calculated using only the input itself. That's why it's called self. Intra Attention. So it doesn't have to be the word that this guy gives as an example in his YouTube video, but it could be any 4-element categorical sequence for this example. I'm saying 4 because all the, in this figures, it will be 4-element categorical sequence. So what we do is, we have the input sequence, 4 elements. So I'm going to call token 1, V1, token 2, V2. I'm naming them V because they have become vectors when I've calculated the embedding for them, right? Because a token is converted to a vector when I do the embedding. So at some step, people have done the embedding for us. Somebody has done the embedding for me. Because in attention, it is the case. Before you get to the self-attention mechanism, there's an embedding layer, which we will not talk about this week, because the embedding layer of the transformer has some specific components that I want to discuss next week, okay? So this is V1, this is V2, this is V3, the vectors. What I calculate is, I calculate the attention between each embedding to the other embeddings in the sequence. So the thing is, I need to have the entire sequence at start. Because if I want to calculate the self-attention of the first token to the last token, I need to have the entire sequence, right? For some problems, this makes sense, like machine translation. It makes sense because I have the entire sequence. Or if I'm going to give you the image captioning example, which the image is provided to me at an instant, and I calculate the sequences of as different regions of actuations in that image, I have it. But for some problems, I don't have the entire sequence. For example, in time series predictions, I don't have those. So maybe the self-attention mechanism is applicable to some domain, but is not applicable to other domains. But forget about it right now. Imagine that at start, I have the entire sequence, just like a text translation example, because when you're translating a text from a language to another language, you have the entire text, okay? So I have these words, blah, 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 blah. What I'm doing is I'm calculating the dot product of the vector. For example, vector 3. Let's calculate the context vector for the third one. I'm going to be doing the same thing for all of them. I calculate the dot products. Dot product is the same thing as Badano's. I will have some scores here, right? Because dot products will give me scalars. So scalar values. So the dot product of the third vector with the first one, third vector with the second one, third vector with the third one. Then I do normalization. Well, softmax or other kind of normalization can be used. Transformer used softmax as well, just like Badano's, just like Chauvet-Tendentels. So you have the weights. And you multiply the weights with the vectors, and you have the context vector for the third one. So when you're calculating the self-attention context vector for the third vector, you're using the third vector with the entire set of vectors. It is totally the same mechanism with Badano's attention, where instead of using the hidden states of the encoder and the current decoder hidden state, I'm using an intra operation. I'm using the entire sequence embeddings with a single input embedding. So the context vector for the self-attention of the third sequence is calculated as this. But for the fourth one, you'll be using V4 here. And the sequence scores, the calculated values will be different and the weights will be different. So the context vector will be different. So in the end, what I do is I provide some embeddings, word embeddings, token embeddings, and I get a context vector. Any questions? Because I think you should be able to follow this since you already know what Badano attention is. I guess not. I'm checking the chats. Okay, simple, huh? We simply find the intra-distance between every word embedding in the token sequence. Well, okay. That product in linear algebra is the projection of a vector into another one. So it is like how similar it is. That was what we've done. And that was what Badano's paper was all about. However, remember, in Chauvet-Tendentel, instead of the dot product, there was a linear layer to calculate those similarities, which was learned. Actually, it is the same in self-attention. We have a linear vector there. To make it a linear vector, maybe if I call these the keys, input vectors the keys. If I call the selected vector for the context the query, the thing I'm trying to find, and these the values, the weighted values, which by using the sum of them, I'm going to be calculating the context vector. I can use a weighting because in this form, there are no weights. And actually, there is no importance of order. This is a bit strange because if there is no importance of order, we lose the meaning of a sequence, right? Transformers handle this sequence thing in another way. We're going to see next week. So in self-attention mechanism, let's think that there is no importance of the order. So transformer will handle sequence order in a different manner, which is the subject of the next week. But in this way, we have no weights, like Badano's simple plane attention. But we could change that. We could change that if we multiply this vector, the query vector, which is the value vector, the query vector, and key vector in self-attention, they are the same, but I multiply them with different matrices. This one with matrix Q, this one with matrix K, and this one with matrix V. For example, if this is Vi, is a 1 by K vector. The embedding size is being K. I multiply it M, any of the M's is K by K. I obtain another 1 by K vector. And imagine this is a learnable parameter. So the Q, V, and K matrices, K by K matrices, are actually a small K by K, because this K is capital K is the key thing. So these are the vectors to be learned in the self-attention mechanism. Because when you learn them during backpropagation, because this is just, you can create a computational graph of it, and we are going to. These are the matrices. Now I have weights. Now I have ways to learn this type of attention. So this K, Q, and V. Okay. So if I put it in a graphical computational graph, which will look like the figure in this paper, it is totally something that you can apply backpropagation to. So you have the vector. By using the keys matrix, you calculate this scores. By calculating queries, you calculate these values. By having the dot product matrix multiplication, you have the scores. And in the meantime, by using the embeddings with the values matrix, B matrix, you use the normalized scores with the matrix multiplication to get the context. Guys, this computational graph explains this structure. Sorry, this structure. And actually, it is the same flow as in the figure, but you don't have these scale because there are two additional operations that I'm going to skip for this week so that you see what plain self-attention is. It is this. So self-attention is nothing but a calculating similarity, intra-similarity within the entire sequence once, okay? So the nice thing about this is when you're calculating the self-attention of an entire given sequence, you don't have to wait for the sequence to arrive because in a recurrent encoder, you first feed the first sequence, the second sequence, the third sequence. The context vectors are calculated sequentially, one after another. But in this one, it is calculated once, but you give the entire sequence in parallel. That's one of the nice things about transformer. Transformer can work in parallel on the entire sequence. That's why every search module, Google or Amazon, use the encoder of the transformer. We'll get there next week. So the key value query concepts come from the retrieval systems, the database field. For example, when you type a query to search for some video on YouTube, which you're trying to find the similarities of that query to the existing videos, the search engine will map your query against the key, so the set of vectors that already exist, their similarity, so that it will provide you the best match videos, which can be thought of the values. So this is that mechanism. So the guys who have designed transformers did design this for multiple purposes, to sequence problems, to search problems, and etc. So the attention operation turns out to be something that can be thought of as a retrieval process as well. Just like I said, that's why it is being used by search engines. So dot product attention can be used, but these guys use this matrices to learn those operations. And what about the sequence order? Just like I said, we'll discuss this next week. Transformers solve that problem before you come to self-embedding. They do some sort of positional embedding. They embed the position information into the embedding vector so that you already have the position information when you're doing the attention. So we'll talk about it next week. This self-attention is actually calculated in a multi-headed manner, which means, I mean, if you don't have these vectors, the self-attention will be calculated using the dot product. And you can think of a single notion of self-attention. But if you have different matrices, the self-attention will be different. Actually, in the original implementation of the self-attention module in transformers, these guys in the encoder use 6 different self-attention modules with 6 different sets of VKQ M matrices, the modulation matrices, these matrices. So that 6 different types of self-attention can be calculated. Why would I need 6 different type of self-attention? Well, it is to represent different things in the input. For example, one maybe represents the similarities of the sequences in the context of time, in the context of place, or in different contexts. So that's called the multi-headed attention. I'm going to stop here because I think this was, again, a heavy week where we understood the concept of attention and different models of attention. And most importantly, the type of attention that transformers have. Next week, when we delve into the architecture of the transformers and the idea that they represent, we'll be ready to solve that problem easily because we'll be prepared with this idea of attention, what attention is. Because if you understand what attention is, I guess you will be able to understand the paper which has the title Attention is All You Need. Okay, Any questions about self-attention?